So we can do that. There we go. We're a little light on people today. Nobody wanted to get up, but that's all right. I'm ready to go back to bed myself, but we're good. So I guess the first thing we'll talk about is, so I'll talk quickly about the group assignments that I put up, tell you about each one of those, and then we'll talk a little bit about this upcoming exam. Yeah, so we'll talk about that and talk about some of that other stuff, and then I'll poll you guys as well. Find out if you want to do another meeting on Friday, because usually we wouldn't do it until Wednesday, but that's going to be the day of the 5th exam. Will be that Wednesday. And I can't do it on Monday or Tuesday because that's when my wife is teaching, unless we do it later at night. So we could either do Friday or like later at night on like Tuesday or Monday or something like that. But anyways, let's talk about the group assignments that I posted there. So the first one was the fluids one. Still admitting people. So there are 2 questions there. Each one of these questions has to do with buoyant forces. Okay. So the first one says that there's a cube of sine length L. It's in made of an unknown material. And it floats between oil and water, where it floats with 72% in the water, and the remaining then is in the oil. So the remaining 28% is in the oil. So basically, your picture looks like, I just have to remember to tilt this up. There we go. So basically, here is the 2 fluids. So here is water, right? So you got H2O down here, and then you got oil up here. And then basically your cube is floating here, where again, 72% is inside of the water, and then the remaining 28% of the volume is then inside of the oil. So what I want you to do then is determine what is the mass of this cube, as well as what is the buoyant force. Okay. So technically here there are actually going to be 2 different buoyant forces. So you're going to have one buoyant force pushing up from the water. So this would be the buoyant force from, say, H2O. And then you would have a second buoyant force pushing upward as well, which is going to come from the oil. So you're going to have FB oil, right? So that the total buoyant force, so FB then is going to be the sum of those 2 different buoyant forces. So the buoyant force from the water less than the buoyant force of the oil. And then since this is in static equilibrium, what you know is that this has to be equal to the mass of the object times g. So in this case, what you know then is that the volume of the fluid being displaced by this portion by the water. So the volume of the fluid then is going to be equal to 0.72 times the volume of the object. And then the volume, which is displaced inside of the oil, like it's coming on. There we go. So the volume of the fluid here, so it's going to be the volume of fluid for the H2O, and then the volume of the fluid for the oil is then going to be equal to 0.28 times the volume of the object. Right? Now here we have to be a little bit careful because we don't know what the volume of the object is, but we do know the mass of the object. Do we care about that? Oh, actually, no, we do know the volume of the object. Never mind, I was thinking of a different problem. Good, where the volume of the object then is simply going to be the length cubed, right? So basically, again, so here, since there are 2 different fluids, those 2 different fluids are going to cause then 2 different buoyant forces. So the total buoyant force will be the sum of those 2 buoyant forces, and it has to be equal to the weight. Right? So for part B, we're then asking for what is the total buoyant force. Well, it's simply equal to the mass times g. So whenever you determine that mass, just multiply that by g, and then that'll give you the total buoyant force in this case. So that's the first one. And then the second one says that we have a block of wood, which has a mass, has a density. So we know the mass and the density, but we don't know the volume. So I was actually thinking of this one. This thing is then loaded with lead so that it floats with 90% of the wood in water. Okay, so let's draw that one. We use green for this one. So here, again, here is the water. So again, here's my H2O. And then what it says is we have some block where, again, this thing is floating such as this, but 90%, so 0.9 times the volume of the object is then submerged. Right? So 90% of the object is submerged within the fluid. Right? Now this is true for both scenarios. So what it says then is, what is the mass of the lead? So what mass of the lead is needed if in scenario A, it's attached to the top of the wood, and then in scenario B, it's attached to the bottom of the wood. So let's talk about each one. So for scenario A, it's saying that the lead is going to be up here. Right? So this is scenario A, and it's asking what is the mass of the lead here. So for scenario A, you only have one buoyant force, and that one buoyant force is going to be acting only onto the wood. So here you're going to have simply the buoyant force acting on the wood. So in this case, for part A, you're then going to have that what? You're going to have the buoyant force then must then be equal to what? The mass of the fluid plus then the mass of the lead, or sorry, not the mass of the fluid, but the mass of the wood plus the mass of the lead times G, right? Lead is what? PB. There we go. So in this case, again, there's one buoyant force. That buoyant force is simply acting onto the wood. There we go. But the total weight that's pushing downward is then going to be the mass of the lead plus the mass of the wood, which is pushing down. Right? So that's the scenario A. Scenario B, you're now going to load it from the bottom, which means they're going to put the lead down here. So in this course, for part B, you're applying the lead down to the bottom. And now you're looking for the mass of the lead in this case. Well, now since you put the lead on the bottom, the lead is also in the fluid, which means that it's also going to feel a buoyant force. So technically here, there's going to be two buoyant forces now. So there's also going to be a buoyant force from the lead, also pushing upward. So for part B, the total buoyant force then is then going to be, again, the buoyant force from the water, on the plus the buoyant force from the lead. And again, all this has to be equal to the mass of the wood plus the mass of the lead times G. Okay. So in the second part where you're loading it from the bottom, it now has to have two different buoyant forces because each one is now feeling a buoyant force because it's now both of them are in the fluid. Where in part A, only one of them was actually in the fluid, the other one was outside of the fluid. Okay. Now in this case, notice also I didn't tell you the volume of the object. I only told you the mass of the object and I told you the density. So you have to use the definition of density to rewrite the volume, right? So again, so for this part, for part B, actually for both parts, doesn't really matter. So in this case, you know, again, the density is equal to the mass divided by the volume. There you go, which means that the volume of the object then is going to be equal to the mass of the object divided by the density of the object. Okay. So in this case, anywhere where you're writing the buoyant force where you need to know that volume, you're going to have to write that in terms of the mass of the object and the density of the object. Okay. Everyone's okay with those? Not too bad, right? Not too bad. Good. So the other thing that I posted has 3 problems on there. 2 of these are technically heat engines, but we haven't talked about those in the video lectures yet, so don't worry too much about those. But these ones are going to use basically all those thermal processes that are in the one video that I posted that talks about first law as well as thermodynamic processes. So let's look at the first one. So the first one says that we have a diatomic gas goes through this particular cycle in a PV diagram where the temperature at A is something, the pressure at A at something, and the volume of A at A is something, while the volume at B is something else. Great. So then it says that the process going from A to B is isothermal, while the process going from C to A is adiabatic, and then the process going from B to C is what's known as isovolumetric. So basically, for part A, it's simply asking what's the number of moles. Well, to get the number of moles, you just use the ideal gas law, because this thing is a gas, which means that because at point A, you know the temperature, the pressure, and the volume, you just say that use that particular point to then find the number of moles. So here you would say the pressure at A times the volume at A is equal to the number of moles times the universal gas constant times the temperature at A. So from there, just solve for the number of moles. For B, it's now asking what is the temperature at B and C? Well, what you know is going from A to B, this is an isothermal process, which means that the temperature is the same. And since the temperature is the same, then the temperature at B has to be the same as the temperature at A, because it's isothermal. Going from C to A, or from B to C, here you have two choices. So if you go from C to A, you know that this thing is adiabatic. And for adiabatic processes, what you know is that what the temperature is related for, so for adiabatic, in this case, what you know is that what the temperature times the volume raised to the gamma minus 1 is equal to a constant. Okay? So in this case, you know the volume at C because the volume at C is exactly the same as the volume at B because that's an isovolumetric process. You know the temperature at, well, you don't know the temperature at C, but you do know the volume at A, and you also know the volume at C. So if you use this expression, you would then say the temperature at A times the volume at A raised to the gamma minus 1 must be equal to the temperature at C times the volume at C raised to the gamma minus 1. So here you can use the fact that you know it's an adiabatic process to then determine what the temperature is. Or again, you can use the ideal gas law and then take the ratio of what you know at B to the ratio at A, or to the ratio at C. Either way is fine. Good. So again, TB must be the same thing as TA because it's isothermal. And then to get TC, you can use the fact that it's adiabatic. Okay. Now, the big long part is part C, where part C says, okay, what is the change in internal energy, the heat, the work, and for now, don't worry about the change in entropy part. We haven't, I don't know if we're going to get that far yet. That may not be something that's going to be included towards the final here, or at least in the next exam. So good. So this is where, again, pardon me, all those definitions of all those different thermal processes are going to come into account. So for example, what you know is what? Whenever you have an isothermal process, then what has to be true is that the temperature is the same, which means the change in internal energy is equal to 0. So what that means then is on an isothermal process, automatically you know the change in internal energy going from A to B is 0 because it's isothermal. What you also know is that in an adiabatic process, there is no heat flow, which means that there's 0 heat going from C to A because it's adiabatic. So by knowing what type of process that it is, you automatically know what is 0 and what is non-zero. And also going from B to C, you know that is an isovolumetric. In isovolumetric, there is no work. So you automatically know the work done going from B to C is equal to 0. So again, by knowing what type of process that it is, you automatically know things that are 0. To get the Q, so for A to B, you know, again, the change in internal energy is equal to 0, so that means the heat is equal to the work. And then you also know that that's equal to N times R times T times the natural log of the ratio of the volumes. And then, what, isovolumetric, in this case, you know, the work, again, is equal to 0, so in that case, you know the change in internal energy is equal to the heat. And then the change in internal energy is just the number of moles times CV times the change in temperature. And then for the adiabatic, so in that case, there's a whole long thing you can do for that. So Anyways, the point of all that is basically knowing all the different thermal processes are going to tell you then what is zero, what's non-zero, and etc. Okay. So one thing that should be true is when you're making your equation card for exam 5 here, those thermal processes should show up on there. They should show up. They should tell you what is equal to 0, what is non-zero, and then the relationships between all that different stuff. Part D, talking about efficiency. So efficiency is, it's 1 minus Q cold divided by Q hot. So basically, you find the lowest Q, that's going to be Q cold. So that's the amount of heat which is flowing actually out of the system. And then you find Q hot, that's going to be the greatest Q. So that's going to be the one that's flowing into the system. And you take 1 minus that ratio, and then that's what's called the efficiency. So the efficiency is basically how well does your heat engine do. It turns out, we'll talk about this in a video, no engine can ever run at 100% efficiency. No engine. It's theoretically impossible for that to happen. The best you can do is what's known as a Carnot engine. Even that, you can never get it to run at 100% efficiency, and this is what's known as the second law of thermodynamics. So second law of thermodynamics says that the efficiency of an engine will never be 100%. It's always going to be less than what's known as the Carnot efficiency, but we'll see those things in the video there. Good, so that's that one. Second problem deals with what's known as mechanisms of heat transfer. So those are some videos I'm going to make today. So you'll see those later today. But basically, there are 3 ways for us to have heat flow from one system to another system. And this one deals with what's known as conduction. So conduction is heat flow when you have 2 systems which are directly attached to each other. So for example, if I had a hot source here and a cold source here, then I would take my spoon. Hopefully you guys can see my spoon. And then I would attach that between my 2 hot systems, cold system. So in this case, my hot system is going to have energy, or in this case, heat flow out through it, through the spoon into the cold system, which is my other hand. And this is what we call conduction. So conduction in this case then is the heat flow through 2 or more objects that are in direct contact with each other. Now, the rate at which this happens and things like that are going to depend on what type of material this is. This, of course, is metal. Metal is actually a very good heat conductor as well as an electrical conductor. So the rate at which this is going to happen is actually going to be pretty high if I'm using something like this. The reason that you put insulation in your house is because insulator is not a good conductor of heat. So in that case, you're trying to limit the amount of energy that you lose to the exterior when you have your heat on in wintertime. And you're also doing the reverse in the summertime. So when you try to cool the inside of your house, you're also trying not to have the heat come from outside into your house to heat up your house. So you want a very terrible conductor of heat, which insulation usually is. Wintertime, some people wear down jackets. Down is also a very bad conductor of heat. And again, you want to do that because you want to keep your inside warm and the outside cold, right? So you don't want to lose all your heat to the exterior. So this one is basically mostly just using with the definition of conduction and how this actually works. So I'm not going to go too much through this one because I'll talk about that in a video today. So we'll talk more about those. But yeah, so this one is actually talking about the growth of an icicle. So you have an icicle which is hanging down. So what's happening then is you have about 0 degrees here, -5 degrees up here. And then what's happening is water then is leaking upward, which is then causing it to freeze up here, which is causing your, causing the icicle then to grow because it's freezing the ice basically at the top. And what this question is basically asking is, it wants you to determine the rate at which ice is freezing and the rate at which the icicle is actually getting longer as a function of time. It's a cute little problem. I like it. It's one of those problems where, you know, you can actually do something complex using the very little bit of the physics that we actually know at this stage. So I like it. It's fun. Good. The third problem basically goes back to, again, another heat engine. So again, this one is, again, a full cycle. So And then again, it tells you the processes going from B to C and from D to A are both adiabatic processes. So again, you know, there is no heat exchange during an adiabatic process. So there's no heat exchange during those. The heat is only going to exchange during the two isobaric processes, which are from A to B and C to D. So from here, it wants to know, is this thing monatomic, diatomic, or polyatomic? So I told you how to do that in a video that I just posted. So basically, you're going to calculate what that gamma term is. So gamma then basically tells you what type of ideal gas that it is. Now I need to remember each one. Anyways, there's a chart in the book that tells you when you solve for gamma. So gamma for different values have then different, correspond to different types of materials. Here, so if you solve for gamma, so in this case, you know the pressure and you know the volume at points A. Actually, know it at all of them. So you know at all the points, you know the pressures. You also know the volumes. So in this case, for that type of adiabatic process, you would just use that. The pressure times the volume raised to gamma must be equal to a constant. So in this case, since you know basically all the different points, you can just say that, say, for example, the pressure at A times the volume at A raised to the gamma must be equal to the pressure at B times the volume at B raised to the gamma. So in that case, you can solve for what gamma is by taking a natural log. Once you solve for gamma, that'll then tell you what type of process that it is. Good. So finally, the last part then is, what is the efficiency of the engine? Well, again, the efficiency of the engine is 1 minus Q cold divided by Q hot. So again, here, there is no heat exchange going from D to A nor B to C because it's adiabatic, which means there's only 2 heat exchanges, which are going to be from A to B and then from C to D. So there, you just want to calculate the heat for each one of those 2 scenarios. And then once you know that, you're just going to take the ratio of those, take 1 minus that, and then that's the efficiency of the engine. Okay. So not too bad. So those are all of those different group problems. So let's talk a little bit about the exam. So this exam is usually a little bit easier than all of the other exams. And the reason for that is there's a whole lot less of me mixing things together, which I usually like to do on all the other exams. So these ones, the questions here are a lot more straightforward than what they are for the other exams. So this will be a lot more of just things like you see in the first problem here for some sort of cyclic process, and then it tells you the different types of processes going from one point to another point. So now basically calculate a whole bunch of things. That's basically what this exam will be like. One thing you'll have noticed hopefully by now is there's a whole bunch of constants on this exam. Lots and lots and lots of constants. So there'll be all those different thermal expansion constants. You're going to have different constants when it comes to conductivity and all kinds of different stuff. So basically, this exam, more so than any of the other exams, is that section where I give you all the constants. That section where I give you the constants is going to be close to almost a page itself. Because you got all the different thermal conductivities, you got all the different densities, you got all of the different thermal conductivities, all the different thermal expansions, basically all kinds of different constants that I have to give you. So specific heats, latent heats, all that stuff. So again, don't write any of that down basically on your equation cards. I'll give you all that on the exam itself. So don't worry too much about those. But yeah, there's going to be a lot of constants, a lot of different stuff that you'll need for those. Hypothetically, this would be the first exam that you would have integrals on. But having said that, all the relevant integrals I've actually already done in all the videos. There's one more we have to do if we get to the entropy part. So even though this would be the first that you would see integrals on the actual exam, there will be no integrals. We'll basically put it that way. Okay. What else? So as far as the material that this is going to cover, it might not cover as far as it traditionally would, because we lost a week due to that extra spring break week, and we only got a day back. Right, that's it. So we were supposed to also get Good Friday back, but because they didn't give us that back because they decided to keep it off, not really sure all the logistics of that. But basically, yeah, the only day we get back is the day that we're moving this test to. So basically we lost, like I said, we lost 4 days and we got 1 back. So we're just not going to be able to cover all the material that we usually would end up covering with thermo. But so by Friday, I'll definitely know. Well, actually later today, I should know what we're going to end up cutting out and not going to be able to put on the exam. So, but I'll talk about that as well in a review video for this. So it should be fine. So I think that's about it. I want to talk about the exam. Well, like I said, typically this exam is a lot easier than the other ones. So this is a good place to basically make up some points if you need some points to make up. So usually it's a good place to make kind of a buffer so that way you can get points and usually not have to do as well going into the final. So it's usually good. So any questions anybody might have for me at this stage?
Yeah. What about lab? Are we pretty much done with lab? Do we have a final in that, or?
No. So basically, yes, we are done with all the lab material. So
Okay.
everything in lab is now done. So yeah, so this week, actually yesterday and the day before, so Monday and Tuesday should have been the lab final. But we aren't doing a lab final because it's kind of a pseudo practical. So we decided not to give you guys a lab final because typically you would have to do part of the lab and then answer questions based off of the results that you get from the lab. But, you know, since I can't send you all that material to make you do it at home, I mean, I probably could, but I'm not going to. They won't let me on campus. Anyways, so I can't ask you to basically do that. So yeah, so there's no way to actually do a lab final. So we decided as a department that nobody is doing lab finals for this semester. So yeah.
Okay.
Yeah, so basically what that means then is, as far as the lab is concerned, instead of your lab percentage being out of 1,300 points, it's now going to be out of 1,100 points. So basically it's just going to be out of all the 11 labs.
So in our normal exam, 5 is Wednesday.
Correct.
Right.
Yep.
Okay. Do you know when the actual final is going to be?
Yeah, I looked that up. That's going to be Monday, May 4th. So
okay.
Basically about a half a week after we take exam 5. Now I did talk about this also in a video. Because that time frame is so short between exam 5 and the final, nothing from exam 5 will show up on the final.
Okay.
Right. So I'm not going to basically test you on the same thing in less than a week. So,
yeah.
Yeah. So that means that the final exam will cover everything from exam 1 through 4.
Okay.
So basically kinematics up through rotational stuff. And we can talk about this later too, if we all decide that we want to meet on like Friday or something like that. We can talk separately about the final. So the final's difficulty is actually typically easier than the regular exams themselves. Mm-hmm. A good place to look for difficulty is the group assignments. So basically it'll be a lot closer to the group assignments as opposed to, you know, a typical exam question. And I'll give you a nudge, nudge, wink, wink. Some of the questions on the final have traditionally come directly off of the group assignments.
Okay.
So a good place to get ready for the final would be to go through all of the old group assignments for the 4 exams. That's right. So the way the questions are more set up are more of, hey, do you remember doing this? And can you show me that you remember what it is and how to use it? So the questions are usually a lot more straightforward. At most, there's 3 parts, but most of them are either 1 or 2 parts. That'll basically be it. So, you know, for example, if it was a force problem, you know, it might be part A, find the acceleration, you know, by drawing free body diagrams, et cetera, et cetera. And then part B would be like, okay, now it has gone I don't know, 3 meters, how fast is it going when it reaches that 3 meters? So just an application of a kinematic equation. So in this case, the third kinematic equation. So, so the final is set up a lot more just, hey, do you remember how this works? And it'll touch all the major topics that we went over. So all the things that are the most relevant. So those things are things like kinematics, forces, conservation of energy, conservation of momentum, and then basically rotational stuff as well. So it only focuses mostly on those big idea type topics, the major things that we should have got out of this class.
Okay.
And that was a lot more of an answer than you asked the question of, but that's fine.
That's good. It's good information.
Any other questions anybody might have towards me? Okay, so let's try doing a polling. I've never tried polling on here. This is gonna be exciting. So ask the question. Oh, do I have to go way back on here? And a question. This looks like more work than I want it to be. Okay, so my question is gonna be, so do you guys want to meet on Friday again? So in that case, we could talk more about the final. We could talk more about the fifth exam if you want to, or any other questions about homework or etc. Or not meet at all before the next exam, or meet later in the evening on Monday or Tuesday. So what do you think? Bonnie, I'll go with you. You're doing a lot of head bobbing, so yeah.
I would definitely prefer like Monday or Tuesday evening.
Monday or Tuesday.
Yeah, because like that gives us the weekend to like get any questions. If that makes sense.
Yes, that does.
Yeah, I'd have to agree with that. We can go over as much material over the weekend, as possible to gather questions, and then we'll have that in our heads right before we take it.
Okay. So, a pen. Let me scribble this down. Send an email to myself. That'd be easier. Okay, so either Monday or Tuesday evening. So, whoops. I started to reply to Alec. Sorry, I almost sent you the email out.
If it ends up being like Tuesday evening, like if I can't make it, then are you going to be able to like record it, or how?
Yeah, that's what I'm actually doing now.
I see the little thing in the corner.
Yeah, because I had somebody say they couldn't make it to this one, so they asked to if I could record it. So yeah, so yes, I can easily record it, and then I'll just post it up onto YouTube. Same thing as before. Give you guys the link to that particular. I think I'd rather do Monday. That'll kind of give you another day instead of just talking about it on Tuesday, because that way, if you talk about it on a Tuesday, that doesn't give you a lot of time between Tuesday evening to Wednesday morning to kind of go over certain things if you need to go over them. So I think I'm more inclined on doing Monday. If that works for everybody else. So, anybody have any objections to Monday evening?
Monday's good for me.
Okay. So yeah, I'll talk to my wife and find out, when would be a good time, but probably something more like 5 to 6 or somewhere around there, 4:30 to 6, something like that. But yeah, I'll talk to her, make sure I don't interfere with her schedule, because she's going to be what's she doing? I don't know when her finals start, so I'll just have to talk to her about that. But anyways, yeah, I'll send out an invite for all that good stuff. So. sent it to the wrong place. Pay attention to these things. Okay.
You said this. You put this up on YouTube.
Yes.
When you record it.
Yeah.
Okay. So is there going to be a link on Blackboard, or do we
Yes.
just?
Yeah.
Okay.
Yeah.
Right.
So when I get it up and I get it on there, I'll send a link to everybody and.
Oh, okay.
Yeah. Yeah, and I'll also do another, video review video. So all the equations and all that good stuff that we need going in.
Okay.
So, any other questions, concerns? Again, anything about lab or anything, class-wise? Any stories you want to share with everybody? I've been working on my culinary expertise here during the lockdown, so that's good. Learn how to make cookies and cupcakes and learn how to grill bread on the grill. So that was cool. I was trying to make
the house down yet.
I'm sorry?
So you haven't burned the house down yet?
Not yet, no. Especially my grill. I'm very good at my grill. But no, I was trying to make what was I trying to make? I was trying to make naan. Came out somewhere closer to pitas as opposed to naan, but it was good. I always grill pizza and stuff on my grill. And, some of you guys in my lab have seen me eating my pizza that I grilled in lab before. So, yeah. Now my cupcakes kind of suck though, because I put too much in the cup. You should only fill it up about halfway to 2/3, and I filled it up more like 3/4, and it kind of exploded over, and the whole inside kind of like dropped down. But it was fine. They still tasted good, so. But yeah.
So you just had a multi-sectional cake. You could get pieces of cake easier.
Exactly. Yeah, and then I made my son had his 5th birthday, so I made his cake from scratch. So that was good. Learning how to do more things, so it's good. It's good too. It gives him something to do. He helps me put all the ingredients together, and keeps him out of trouble. So we're good. Yeah, but no burning down the house yet. Not yet. Sure, if I'd let my son cook, that would happen, but that's fine. How are all your other classes going? Are everything finishing up okay?
I would always prefer to be in person and
Oh, yes.
and do that. Yeah, but yeah, that's the way it goes.
Yeah. This is a very weird time. Yeah. So.
I feel like there's way more work now, like between learning lectures like on our own and then the homework that's already assigned. I feel like it takes so much longer.
Really? Okay. Gotcha. Is that because the videos are longer, or?
I mean, I don't know. It's hard to like stay on track. It's easy to get like behind. And so, I don't know, part of like the discipline of it. And then I do feel like it's longer because I have to like pause the video and write and then like listen and comprehend versus like if we were in class, we'd do it all at once. So that's just my problem. I don't know if anybody else struggles with that, but.
Yeah. And you can always interrupt me during class where you can't really do that in the video lectures. So do I talk faster in the videos or about the same?
I don't know. I put you on 1.5 speed, so you kind of have a higher voice. But
I have a high voice to begin with. Yeah. Nice.
I think my English class just kind of like stopped. Like we wrote our last paper a couple weeks ago, and we haven't done anything since.
Oh, really?
I don't know what our teacher's doing, Shane, but it's not good.
Doesn't sound
You
very
email
good.
her and she ignores the fact that you emailed her, you ask her questions and she doesn't answer.
Yeah. I don't know if she's just busy but I haven't gotten an email from her for like a week now.
Okay.
She goes, let's have a Zoom, and then we all get on and we're all confused and the Zoom isn't actually opened, and it's a good time.
I never got to tune in for that, but that sounds great.
Wow.
Sleeping too much is hard.
Gotcha.
I'm gonna hop off because I have a chemistry exam in like 20 minutes. So
That's fine.
thank you.
You're welcome. Yeah, I don't think we have much more to talk about anyway, so I think you're fine. All right. See you, Molly.
Yeah, I should probably go too. I'll see you later.
Okay. See you, Shane. All right. So, any other questions, concerns anybody has, or everybody doing okay so far? Like I said, this exam is usually easier. So again, it's a good place to kind of make up some points, and if you need any, if not, it's a good dropped exam too. So you don't have to worry too much about it. But yeah, like I said, it's usually a little easier. Like I said, at this point, I don't know exactly how much we're going to cover. I'll be talking to Dr. Merlot this afternoon, so we'll decide based off of where he is in his class and where we are in our class and how much of the material we'll have to kind of cut off. Then from there, once I know a little bit better, I can put another message onto Blackboard, kind of let you focus a little bit more on what types of things that you'll see. And again, I'll do a review video as well, so we can talk about it then. And again, so we'll meet Monday. Again, something more like 4:30 or 5 o'clock. So we could talk more about the 5th exam, and we'll talk some more about the final as well, since we don't have that much time between then. And as always, if you need to talk to me, have any questions or anything, just we'll set up a Zoom appointment and go ahead and talk, or bombard me with a bunch of emails. That works too. So, okay. What kind of dog is that?
It's a Great Dane.
That's a Great Dane.
She's so needy. Yes.
That's all right. My daughter never lets me put her down when I pick her up, so it's fine. It's about the same.
What kind of dog do you have?
Oh, my daughter, not my dog.
I am so sorry.
Okay,
yeah,
Vanya, maybe I take that back. Maybe you're not going to have kids anytime soon.
To fill you in, me and Dawson have a bet going on.
Gotcha. Nah, she's 2. All this morning I was trying to make my breakfast and their breakfast, and every time I put her down, she's just doing this and then throwing a fit that I'm not picking her up right away. So, yeah. Can't really go and do anything by myself, but it's fine. All right. Okay, well, I guess I'll let all of you get on around with your day. So have a good day, and I'll see everybody on Monday. And yeah, we'll go from there. All right.
Bye.
Bye, everyone. Bye.